Livestream auf YouTube. That's going. Oh. This one. Meeting prepared. It's gonna be there. All right. So back to the Zoom. Fertig. Yes. Schirm. Time. My phone eye. Yeah. Right. Back to the Zoom. Fertig. What is Schirm. Time. My phone eye. Yeah. Right. Back to the Zoom. Fertig. What is Schirm. Time. My phone eye. Yeah. Right. Back to the Zoom. Fertig. What is Schirm. Time. That's my phone eye. Yeah. Right. Back to the Zoom. Fertig. What is Schirm. Time. That's my phone eye. Yeah. Right. Back to the Zoom. Fertig. What is Schirm. Time. That's my phone eye. What is Schirm. Time. That's my phone eye. What is Schirm. Time. That's my phone eye. What is Schirm. Time. Yeah. That's my phone eye. What is Schirm. Time. Yeah. That's my phone eye. What is Schirm. Yeah, that's microphone on. You know what channel yeah, that's microphone on. You know what let's take a look at the channel yeah, that's microphone on. You know what let's take a look at the channel yeah, always Zoom microphone on. You know what let's take a look at the channel yeah, always Zoom microphone on. You know what let's take a look at the channel yeah, always Zoom microphone on. You know what let's take a look at the channel yeah, always Zoom microphone on.
So it's time now, okay, so that we
let's take a look at
would
the
not
channel yeah, always Zoom microphone on.
So it's time now, okay, so that we
let's take a look at
would
the
not
channel yeah, always Zoom.
right. Yes, we have to start our lecture right now so that we will not based on the thought to leave for rest or class participation is to write down at your write down into the chat box in the Zoom or in YouTube, okay, as the M604 student have done. Okay, you just write down your name also in the YouTube channel and capture your screen or monitor, okay, and send it to the live chat box, okay. So that's also a possible way. We am now trying to let you get into the Zoom meeting. So okay, yeah, you can simply type your name in the chat box in the Zoom, okay, or you can also write down your name in the in YouTube channel, okay. In both channels, I have provided you the direct YouTube channel or the reflected one from the Zoom, okay. It's also possible. If I move to the Good Note page, I may not be able to see your appearance. You're asking. You're asked to enter. Okay, your request to enter the class. So well, and yes, some of you are waiting for the permission to get into the lecture. Okay. Yeah. We will talk about the story in this one, right? In I think we we have already seen the gravitational force, right, of the conductor, right? Yeah. Now ทุกคนได้ยินเสียงผมนะครับโอเคไหมครับyou can hear me yeah. Let's add this topic in okay, let me prepare. We arrive at this topic in okay, so that's everything is clear enough. All right. Well, yeah. Before that, you have seen อย่างvalue นะครับโอเคไหมก็คือโอเคไม่ว่า Zoom หรือว่าที่ YouTube ก็ได้นะคุณพิมพ์ที่ YouTube ก็ได้ถ้าคุณสะดวกดูที่ YouTube บางอย่าง604นะครับเขาก็บอกว่าเขาอะไรนะเขาไม่สะดวกที่จะเข้ามาที่ Zoom อย่างเงี้ยก็ไม่เป็นไรใช่ไหมคุณก็ดูที่ YouTube ไปเลยแล้วคุณก็พิมพ์ชื่อใน YouTube เพราะผมไม่เช็คที่กล้องแล้วมันเสียเวลานะผมอยากเอาเนื้อหาคุณไปให้จบ4บทอย่างเร็วๆนะเพราะว่าเทอร์โมไดนามิกพวกฮีทอะไรพวกนั้นนะโจทย์เยอะนะครับปีที่แล้วก็ไม่จบนะครับโอเคyes we have before you have seen the story about single conductor, right? And right now we are going to see something about the two conductors. Okay, there are two conductors in this scenario, and before that you have seen the FILB, right? When there is magnetic field passing through the area of that conductor, you get the induced force, right? Yes, the outcome or the output in yes. But right now we will see more realistic situation when we have two conductors. Okay, let's say this is okay. We arrive at the slide number 96. Okay. Okay. We are now talking about the slide page number 96. All right, and it's the story, the topic of magnetic force. Okay, actually magnetic forces. Okay, between two conductors, but both forces have the same. You will see at the end that both forces have the same amount. Okay, the same magnitude. So it's also possible that we simply say it's magnetic force in singular form. Okay, but actually there are two forces in this topic. All right. Yeah. Right now we have two forces. Two conductors. Let's say the upper one is conductor number 1, and the lower copper wire is the second conductor. Okay. It may not be made of copper, but I usually say copper wire, right? Okay. นะครับพิมพ์นะครับคนมาใหม่นะครับคุณจะพิมพ์ที่ในแชทบ็อกของ Zoom ก็ได้นะครับแล้วก็คุณจะพิมพ์ที่ YouTube ก็ได้นะสำหรับคนที่อยากดูที่ YouTube เพราะผมส่งลิงก์ให้คุณทั้ง2ลิงก์แล้วนะครับที่ลิงก์ของ YouTube แบบสตรีมตรงๆนะครับจากคอมพิวเตอร์นะครับมันจะชัดสุดนะแต่ว่าเนื่องด้วยอินเทอร์เน็ตมันไม่ค่อยแรงนะมันก็จะกระตุกหน่อยนะครับผมยังไม่รู้ว่าโซลูชันที่ดีที่สุดมันขึ้นไม่แรงมากเนาะดีที่สุดเนี่ยจะเป็นอย่างไรนะครับมันยังกระตุกอยู่นะครับวิ่ง310เนื่องจากว่ามีคนแย่งสัญญาณอะไรกันนะครับ another link is the YouTube, that is the result from the reflection by the Zoom. Okay, it just reflects all the vision or the screen from Zoom, okay, to the YouTube. Okay, if you are not convenient with the Zoom, okay, you want to be free alone, or for any reason, okay, you can also watch this watch our class in the YouTube link. Okay, let's continue our story. We have two conductors, the first conductor and the second conductor, okay, the upper one and the lower one. But we will pay attention first to the force that happens at the upper conductor first. Okay, you will see later the force that is exerted that exerts on the second conductor later. All right, here let's say for simplicity, at the first case, okay, we assume that the current flows in the same way, in the same direction to the through both conductors, okay, from left to right. Okay, for generality, okay, we assume that the first conductor has the current of amount I dash, okay, I prime from left to right, like this. In is denoted by I dash, okay, and the lower one, which is the second conductor, let's say it's the amount of the current is denoted by I, okay, without prime or without dash. All right, and they just use I and I prime so that we can have any value for those two amounts, okay, for those two currents. Okay, and it can happen that both current can have the same magnitude. Okay, it can be possible as well. Okay, back to good note. Yeah, but we will take a look first at the force that would happen at the upper conductor, which is the number one, okay, number one conductor. All right, okay, yeah, okay, one thing I need to mention is the type of the symbol. Okay, the symbol you would see here, this is the box, right, the cubic box. In it's not it doesn't appear actually, but they just draw the box so that you can see some cross-sectional views in different planes. Okay, for example, this one, we have 3 planes. This plane, right, this plane which has many dots into that, and another plane is the horizontal. Okay, another plane is the lower one here. All right. Yeah. Okay, and the vertical plane, another vertical plane. Another plane is the one here. You can see easily the line, right? The lines, so many lines here, and that line is the magnetic field line. Okay, and those are magnetic field lines. There are several lines, and this will be the result, okay, from the former topic that we have seen, which is the magnetic field, okay, induced by caused by the current flowing through a long straight copper wire, right? And the way we could find or determine the direction of the induced magnetic field is the use of right hand, right? We can use the right hand to find the direction of the induced magnetic field, right? In physics, we have to take care of both things, right? The direction and the magnetic field, right? In order to find the magnitude, sorry, we have to find two things, right? The magnitude and the direction. And in order to find the magnitude, we have to apply the Biot-Savart formula, right? If you can remember Biot-Savart formula, it's B equal
ต้องกินอะไรบ้างอะเลข
B equal mu 0 I, right? Mu B equal mu 0 I and 2 pi R, right? That's the Biot-Savart formula to find the magnitude of the induced magnetic field in several scenario, but this is the special case of what may happen related to magnetic field and current, right? Of course, we let the current flow from left to right in the upper in the lower conductor, right? Of course, if you lay your thumb, okay, in the same way as the current direction, you will find that your remaining 4 fingers are gonna give you the direction of the induced magnetic field, okay? And if you take a look at this cross-sectional view, you see many dots right here, okay, on this plane. And as I told you, the dot sign, the dot symbol means the head, okay, or the front part, okay, the front view of any vector quantities, right? And you see that the magnetic field will be will point at this plane, okay, at this location, out of the plane, right? Because we see the head view or the front view of the arrow of the vectors. It's the head or the front view of the magnetic field at this plane, right? And on this plane, you can see the cross signs, which are the X sides. It's the rear part, okay, the rear part or the back part of those vectors. Okay, there are many cross signs. It means there are many vectors around here. And if you take a look at this plane, you will see that you can see the curve, right? So many curves on this plane, right? And they also provide the arrow, which means the magnetic field in this way, okay? But there are many lines, okay, not a single line. Okay, it depends on how far you it depends on the location or how far you are from the lower conductors. Okay, now you can completely see what's going on in this figure. Yeah. The important thing that happens in this figure is that when you take a look at this location, okay, we are now moving to the conductor, and we will see what will happen to the first conductor, the upper conductor, right? The lower one is the second conductor. Okay. At this location, you will see the same direction of the magnetic field. Okay, you see the front view, okay, front cross-sectional view, or the rear part of that vector. And you will see that the vector at this location, the vector of magnetic field is going to point like this, okay, out of the plane. Okay, but if they draw this figure into the, we could not lose. We may lose some information. That's why they draw it in a different angle. Okay, so you can see that this is direction of the induced magnetic field. Okay, caused by the lower conductor. And as you have seen in the previous topic, F, right, is I and L cross B, right? That's the first step in order to find the induced force when there is current moving through along the copper wire, right? And in that area, there is magnetic field, okay? Yes, in this area, we have magnetic field, and there is also current moving through this conductor, okay? Forget about the lower conductor, okay? The lower conductor just gives you the induced magnetic field, okay? But the important thing is the upper one. And when we have the current moving through the upper conductor or the first conductor, and in this area, there is also magnetic field, okay? With the vector B pointing out of this plane, okay? The wall, okay? This is the wall, the first wall, and here is the second wall, okay? And here is the floor, right? Okay, in this room. There is a magnetic field from this wall, okay? And yeah, we are going to determine the possible direction of the induced force that may happen. Okay, the first vector is L, right? So we write down L, vector L. Where is L? Okay, L will be the vector that follow the same direction as the currents. Okay, the violet one here. Okay, so L vector will be will point in this way. Okay, in the same way as the current in this conductor. Okay. Okay, in this connector. Yeah, and that's the first vector we have to mention. And let's talk about the second conductor here, right? It's vector B, right? And yeah, where is B in this location, in this area? B is going out, okay, of the wall of this plane, right? So vector B will be this one, right, out of the plane. Okay, that's the vector B, the green one here, which is what I write down. Okay, and yeah, we have two vectors. We have to turn or rotate our four fingers from the first vector to the second vector, right? And yeah, from the first vector L to the second vector B, okay, you use your four fingers and you will find that you will get the outcome, which is the vector of the induced force. Okay, we get it like this, downwards. ถ้าคุณใช้มือขวาครับ that's the induced force that happens at the upper conductor and the first conductor. All right. Well, yeah, now you are able to determine the force, right? The force is directed downward. Okay, is pointing downward to another conductor, right? Here, the I don't know, the pink or the red vectors. Yeah, okay, that's the force F. Okay, now let's move to another one. Okay, to another figure, figure 43. You find that it's not different at all. It's the same configuration as figure 42. All right, but this one has no box, has no walls or floor at all. Okay, you can see the spinning circle, several spinning circles that represent the induced magnetic field caused by the lower conductor. All right, yeah, the spinning circle means the induced magnetic field lines given by the lower conductor. But for I don't know, fortunately or unfortunately, there is a line that hits exactly the upper conductor, and this causes the induced force. Okay, and the way to find the direction of the induced force has been already explained to you. All right, and now we move to another figure. Okay, the former two figures are taken from the same book. Okay, but this one is taken from another book, so they use a different configuration, but it's the same thing. Okay, the same principle, the same idea. You have the first conductor at the upper position, and you have this. You have the second conductor at the lower area. In the currents, there are two currents. Okay, moving in the same direction. Okay, from left to right, like this. All right. From left to right, and the two conductors are separated from each other by the amount of D. Okay, by D. Okay, D is a positive number. So they simply say I1 and I2. Okay, but in the former two figures they say I and I. That's right. It means in those two conductors, we can have different values for the currents. Okay, in the portion of the conductor that we consider in this topic is only on the length of L. Okay, we don't consider the conductor with infinite length. Okay, with infinity length. Okay, so but this figure give you more tidy one. Okay, it's better to understand. It's easier to understand because they just draw only a single green circle here. Okay, single green circle means the induced magnetic field line. Okay, and this is the line that is significant. It just upper conductor. Okay, and okay, of course I2 is moving from left to right, and if you lay down your thumb in the same direction as I2, your remaining four fingers will give you direction of induced magnetic field, which is pointing out of the plane. Okay, but they draw this figure in a different angle so that you can see all the information. Okay, if they draw it in 2D, you will not see it easily. Okay, that's the induced magnetic field given by another conductor. Okay, it's not the magnetic field caused by its own conductor. Okay, this is the magnetic field given by the lower conductor. So that's why they say B with the subscript number 2. Okay, B with subscript number 2 means that this is the magnetic field. Okay, given by the second conductor. Okay, it's not B1, it's B2 because B2 is the result from the second conductor, the lower conductor. Okay, in yeah, L is the vector that represent the direction of the current, right? In this way, at I1, that's the vector L, and vector B is this one. Okay, it is pointing out of the plane or from a little bit right to left. Okay, and here is vector b2 right, and you can get the outcome or the output as the f. Okay, f1. Why do they provide a subscript number 1 to this scenario? Because this is the first taking place at the first conductor, okay, at the upper conductor. So that's why they say number 1 as the sub in this figure. So yeah. Now let's move to okay, the magnitude in this one is magnitude in this one is the magnitude of the f1 is I, right? Which I1 as well, because it's the current flowing in the upper conductor or the first conductor, and L, right? L is the same, okay, for both conductors. We don't consider the case when the length of the conductors are different, okay? We consider the environments where the conductors are cut with the same amount of length, okay? And B will be the magnetic field caused by another conductor, which is B2, right? The lower one. And there is also a side term, right? Side theta. But as you can see from this figure, you will find that the angle between those two vectors here is the right angle, right? It's 90 degrees. So theta is 90. So sine theta sine 90 will be simply number 1, right? Right. Okay. So we don't need to pay attention to this term at all. It's going to be number 1. So that's why they say it's equal to I1 and L and B2, right? Okay. Please note that B will not have the same subscript, okay, because that's the magnetic field given from another conductors, from the conductor number 2, right, the lower conductor. So let's move to another page. In here is the result that they have provided. Yes, it's F1 is I1 and L and B2, right? Oh, อินเทอร์เน็ตไม่ค่อยไปเลยนะครับสำหรับอันนี้ใช่ไหม Okay. All right. We are now ready to change this one to all right. Now, but the expression F1 equal I1 LB is not the final result. So we have to go ahead with the final results from this one, right? So yeah, what should it be in this case? We will see it later. นะครับตอนนี้อินเทอร์เน็ตไม่ค่อยไปแล้วเดี๋ยวผมเช็คนิดนึงครับ we will use the former results given by the Biot-Savart formula, okay, so that we will get the real final results from to what we get here. Okay, all right. F1 is I1, LB2, right? In from what we have seen earlier, the magnetic field caused by the lower conductor, for example, in figure 43, B in this scenario is mu 0 I, right? Mu 0 I, and it's going to be mu 0 I. B will be mu 0 I, and divided by 2 pi R, right? But R in this case is R, right? And for this figure, we have D, right? So we are going to write down B is equal to mu 0 I, mu 0 I, and 2 pi and D, right? So that's the magnetic field according to the Biot-Savart formula, right? We apply the Biot-Savart formula. All right. Okay. Yeah. Then we substitute Biot-Savart result into the FILB expression, okay, so that we will get complete final expression to that. All right, and yeah, you can see that B2 is over there, right? And B2 is also here. Now it's time to move B2 to that location, okay, and F1 will be I1, and F1 will be I1L and B2. All right. Okay. L and B2. All right. And we will replace B2. We will replace B2 by the result from Biot-Savart formula, which is mu 0 and I2, right? And divided by 2 pi D. Okay. What is the reason? What is the reason why we use I2 in this case? Because B2 is the induced magnetic field caused by the current in that conductor, okay, which is denoted by number 2, right? The second conductor. So we will have several. To the right hand, right? It's going to be magnetic field line like this, okay, with different location. Okay, that's the B2, right? B2. So the magnitude of B2 would be computed from the magnitude of B2 will be computed from the I2. So the I2. So that's why we have I2 in equation 41. All right, and after, it's not complicated or difficult mathematical expression, right? I1 times L times mu 0 times I2, right? You leave everything at the denominator, okay, and something at the lower part will stay as the denominator, right? So you're gonna have some mu 0, I1, I2, right? And L, okay, at the end, divided by 2 pi D. All right, and that's it for the result in this case. All right. So now let's move to another page, okay, that is what you can see here in equation number 42 give you the idea why we are here. Oh yeah, that's the induced or exerted on the first current. All right, it's not to understand, right? But you could see this is the force. What about the force that may happen to the second conductor? Is there any force taking place at the second conductor as well? Right, because in those three figures, they just take a look at only the force at the first or the upper conductor. All right, and then you may wonder that is there any possibility that we have the induced force as well at the lower conductor or at the second conductor? Is it possible? The answer is yes. There is also induced force taking place at the lower conductor, at the second conductor. Okay, and if you use a same manner in order to derive or to get the results, you will find that the lower conductor will have the same amount or same magnitude of force, induced force, as the force in the upper conductor. Okay, it's the result in equation number 43. Okay, I will give you the idea why we arrive at equation 43. Well, you have here two conductors, right? And sorry, I need to use different colors so that you can easily understand. That's I1, right? The first, the upper, yeah, that's the I1, and here is the I2, right? I2 current in yeah, you can have the induced magnetic field like this, right? And that's the result from the first conductor, Okay, it will provide B1 as well to the conductors like this. All right. เดี๋ยวนะผมเช็คนิดนึงว่าทำไมภาพไม่ไปเลยนะครับที่เครื่องนึงนะ because they use different Wi-Fi. All right. Use this one. They have to use X to XG. All right. Okay. Now we will see whether there is how strong the force is going to happen at the second conductor. Okay. All right. We need to find again the direction first. F2, right? Is I would be I2, right? And vector L at the second conductor cross vector B at the second conductor, but the vector at the second the vector of magnetic field at the second conductor is B1, okay, because that's the magnetic field given by the first conductor, right? At this location, you find that the L vector is going to be somewhere here, right? Is pointing from left to right like this. That's the vector L. And what about the vector B? Vector B will be the vector pointing into this plane, right? Into this plane. And that's the vector B. But our target is to find the induced force, right? You have to turn or curl your four fingers from vector L to vector B, from the first vector to the second vector. And you will find that after you use your right hand, you're gonna get the induced force pointing upward like this. Okay, that's the F number 2. Okay, before that, the force at the first or the upper conductor has direction pointing downward, right? But this one at the lower conductor pointing upward, okay, in the opposite direction. Even we let the current flow in the same way, in the same direction, okay, from left to right. Yeah, with this configuration, okay, the upper conductor has the force pointing downward, and the lower conductor has the force pointing upward. So we can conclude that this is the type of attractive forces. Okay, this is the simply speaking, they are the attractive forces. Okay, the force that try to keep or make both conductors staying together or close to each other, right? It's attractive force. And yeah, on page 101, you may notice that the currents in those two connectors are in the same way, okay, are moving in the same direction. And this will give us the attractive forces, right? But what happens if we have the same configuration of two conductors, but we let now the current flow in the opposite direction? For example, the upper one has the current flowing from left to right, but the lower conductor has the current flowing from right to left. Okay, those are in opposite directions, right? Should the force will be again attractive or not? Or what is the opposition? Another sense of attractive, it should be repelling, right? Repelling, or something that try to keep or move two things away from each other, right? So should this force be attractive or repelling? So after you use the right hand rule to both conductors, you will find that the output from this type of current movement, right, in the opposite direction, will give you the repelling forces. Okay, the force will be will point in the opposite direction. Okay, again, okay, this is F number 1, right? This is F number 2. Okay, these are repelling forces. Okay, they try to keep those two conductors far away from each other. Okay, but before that, the force try to keep those two conductors to stay closer to each other, right? Okay, let's make a conclusion on page number 102. Okay, and we will see the relationship as well to the former topic. Okay, before that, we don't have the we don't have another conductor. Okay, we have only a single conductor on the left side like this. All right, we have a single conductor like this, and there is no force happening at all, right? All right, there is no force that happens at all in this configuration when the current flows from the lower part to the upper part. Okay, the current is going upward like this, and there is no force induced at all. And if you take a top view to this figure, you will see that the dot line, right? The dot line means you see the front view of that vector. So that's why you can see only the dots, right? And you see turning, okay, or circulating vectors like this. Okay, it represents the induced magnetic field. Okay, after you use the right hand rule, okay, you find that your remaining 4 fingers are going to be I'm going to give you the direction of the induced magnetic force, but there is not only single magnetic field lines. Okay, totally, we don't have induced force at this one. Okay, and if you want to find of the induced magnetic field, can apply the Biot formula. Let's move to another figure at the middle here. 2 conductors, and the current at those 2 conductors are moving in the same direction, are moving upward like this. Okay, and let's take a look at the top view of this figure. Okay, the middle one, you will see the result at the lower part here. Okay, you find that of course, after you use your right hand to each conductor, you will find that the magnetic field line is going to point like this. But when those 2 closer to each other, the magnetic field line will merge to each other. Okay, we combine to each other, and you have a single line of magnetic field line like this. Okay, it's not simple circulating magnetic field lines anymore. It's the combined version, the combination of adjacent magnetic field line. Okay, you have a single magnetic field line. Okay, it's I don't know what is the shape, how to say in English, but it's the combination of magnetic field lines. But the important thing in physics for us is the force, right? Because that's a potential effect that can happen in nature. Okay, the force in this case, okay, you can see that you get the dots at the center of each component, right? Because that's the head or the front view of the vector of the currents, right? And after you use the right hand to each conductor, you find that you get the attractive forces like this. Okay, when we let the current flow in the same way. And let's move to the right one, the third figure. We let the current flow in the opposite directions. For example, the left one has the current moving upwards, and the right one has the current moving downward like this. And after you apply, let's take a look first at the top view, a cross-sectional view, top view of those 2 conductors. You will find that magnetic field line now has different manner. Okay, after you use your right hand, you find that the magnetic field line is going to turn around like this. Okay, at the first conductor, but at the right conductor, but at the left conductor, you use your right hand, is going to give you the magnetic field line turning in the clockwise direction, right? This is the clockwise direction. But on the right side, you have the magnetic field line turning or circulating in, this one is, the left one has the magnetic field line rotating counterclockwise. I'm sorry for that. I get confused. คือไม่ได้สับสนนะเพียงแต่ว่านึกคำพูดภาษาอังกฤษผิดครับใช่ไหม and on the right side you get the magnetic field line. Where is my mouse? Okay, you get the magnetic field lines turning clockwise, okay, and at the meeting point, okay, the area between them, okay, you get the superposition, okay, the summation of the forces is not going to be the merged version or the combined version. It's going to be the area that has very strong magnetic field pointing upward. Okay. In after we have the current flowings in different directions, you apply the right-hand rule to FILB, right? FILB vector version, and you get the direction of the forces to each to both connectors, and you find that the force is of the repelling type. Okay, the forces try to keep those two connectors away from each other. Okay, it's repelling forces. They are repelling forces. ผมขออนุญาตไม่ได้เข้าห้องน้ำเลยครับปัสสาวะนิดนึงครับขออภัยนะครับ Okay, we have to leave this lecture at 11:30, right? So that you can have the break of 20 minutes, okay, according to the school policy. Okay, now we arrive at the first example. Okay, that's the first case that we can apply what we have talked before. 605นี่เร็วมากครับไม่ต้องเสียเวลาเซตอะไรนะตอนเบื้องต้นทำให้คุณมีแนวโน้มว่าจะนำเขานะครับ Okay, all right. Well, the example is taken from the book number 2, example 19.8. In the story is the following. There are two wires. All right, there are two wires. Two conductors. Let's say, okay, in horizontal way like this. Okay, two conductors, and each have each has weight per unit. Oh my God, what is that? Weight per unit, like we haven't talked about before. Yeah, anyway, we have to go ahead with the instruction by this example. Weight per unit length of 1.10 raised to negative 4 Newton per meter. Why is that? Okay, let's take a look at any conductors. Okay, like this. When you cut it or you consider only the part that has the length of 1 meter only, okay, the conductor may be quite long, but the weight at this location only, okay, will be sorry, right, will be 1 Newton, okay, not 1 kilogram, okay, it's weight, okay. It includes already the gravitational acceleration on Earth, okay, it's weight, it's in Newton. So if you cut it or take a look at only one, oh my God, sorry, what time? Hello. ข้างล่างเลยครับ